everyone. I am Assistant Professor Urmi Shah from IT/ICT Department of LG Institute of Engineering and Technology. In the previous session, we had started with the pulse modulation technique chapter, which is our chapter number 6 of analog and digital communication. So basically, now from analog communication, we are moving towards digital communication module. Like why we are replacing analog and we are moving towards digital communication, that we have discussed already in our previous sessions. As we have discussed the limitations of analog communication and the advantages or the future enhancements in the field of digital communication system. So now let's move ahead with the following topics in this module. So in this session we are going to cover following topics. That is, so these are the following topics which we are going to cover in our today's session. So the topics which we are going to cover is quantization, then error generated by quantization process. Basically, what is quantization and what are the factors which are going to affect the process of quantization, that is the quantization noise. Everything we will be discussing in detail, and then we will be discussing about the two important concepts of the quantization process, that is compression and expansion of signal, which will be done by using the compounding process. So that we will be discussing, that is the use of compression and use of expansion via compounding process, that we will discuss in this session. So following are the topics which we will be moving ahead in the session. Let's start with the first topic. So basically in quantization, we are going to see the discretization of our signal. Basically whatever the source signal we have is in form of analog nature, that is continuous in waveform. So to convert the discretized digital samples of analog or continuous signal, we need to perform the quantization process. Basically, quantization is the process of changing the continuous amplitude signal into an discrete amplitude. That means if I have a continuous wave and if I want to sample or discretize the wave in form of some discrete points, then at specific interval of time I have to check the amplitude of that corresponding signal. So that is conversion of continuous wave into discrete form, that is we called as quantization. As you can see over here, the continuous waveform has been discretized in form of some specific amplitude at specific time interval, that is known as quantization. So this process is very much important in the field of digital communication whenever we are performing the digital transmission of any signal via some application and we require the source signal as our analog signal. These quantization process is frequently used. Now moving ahead, this was our quantization process, and nextly we will be discussing what are the corresponding amplitude values or codes which we called as pulse code. So basically one of the example has been presented to all of you over here. The example says that if you want to communicate sampled values and we have to send a sequence of bits that can represent some quantized value. For example, here 16 quantization levels has been shown to you, that is from 0 to 15. Total 16 quantization levels which require 4-bit data at a time has been represented over here. Now TCM can be used as a binary representation of values. So here we can have, like, if your first binary equivalent of digit 0 is 0000, that means your pulse will be low everywhere, as you can see over here in the first example. While in the last example, as you can see here, if you have your pulse code as 1111, then your pulse code waveform will be high for all the 4 bits. So this way, our 4-bit binary pulse code representation can be done via such an example of quantization. Now moving ahead, basically whenever we are moving at stage 2 of quantization, we will start with a sampled signal. Sampled signal means if you have a continuous waveform, I am discretizing it in form of sample, converting the digital sample from analog values. So that is a sampled signal. We will start with a sampled signal, which we call it as m of t, and then I want to quantize that sample signal. So that is our stage 2 of quantization. Moving ahead, the quantized amplitude is limited to a certain range, that is from minus m to plus m. It will be having some range of variation where and where only our signal will be represented. So it can be between certain range, and if you can extend it, then we can extend our range. Now we need to divide the range in specific time interval. If you are having a range from minus 5 to plus 5, then I need to divide it in 3 half or 4 half, that is from minus 5 to minus 2, from minus 2 to plus 2, and from 2 to 5. In such a way, I have to divide it in form of uniform spaced interval. Then the number of intervals will be represented as an L variable. Let's take an example. My range is from minus 5 to plus 5, and I am dividing it in 3 uniform sections. So my L value will be 3, as I have taken number of interval as L. And the separation between quantized level will be represented in form of delta. Delta is the variable which is going to be represented as twice of m of p divided by L. M of p will be our maximum range value. That is, our range is from minus mp to plus mp. So total our range is twice of mp divided by L. L is the number of intervals. So this way how our quantization variable or separation variable will be defined in terms of delta. Then the kth sample of our signal m is going to be designated as m of kts, and it is going to be assigned some value which will be equal to the midpoint value of the two adjacent levels. So over here you can see that m of kts is our kth sample value and m cube of kts is our kth quantized sample value. So this is the difference between simple value, that is our sample value, and further after quantization whatever it will be generated, it will be our kth quantized sample value. So our quantization error. Now what is quantization error? Whatever I am passing in form of signal, in form of sample, same thing should be quantized. If the levels are different, that is the subtraction of two signals is different, that means there is some level or error in the values of the amplitude. So here if I am performing m q of kts minus m of kts, that is the difference between the quantized message signal and sampled message signal. So if that error value is some finite, then there are chances of quantization error. There can be error generation while performing quantization. So this way we will have quantization error. Moving ahead, nextly, this is our error generation process. How error will be generated? You can look over here. Basically, this is our waveform, and as we have defined that quantization noise Q of t is equal to M of t minus MQ of t. So here the difference will be going to generate the quantization noise. This way we will have the graphical representation of quantization. Our continuous waveform is our sample value, and the staircase kind of waveform is our quantized value waveform. So this way we can have error calculation while performing the process of quantization. So nextly, at the third stage of quantization, what is going to happen is the quantized levels are going to be separated by delta value, that is 2m of p divided by L. The maximum error which can be generated over here will be 1 by 2 delta. So the time average mean square quantization error will be delta square by 12. How it is going to be generated? That is Q square is our mean square formula, that is MP square by 3L square. So it will be delta square by 12. So this way the mean square value can be generated based on the quantization noise value. Basically, NQ is our quantization noise parameter, which is equal to Q square. The NQ value is directly proportional to the fluctuations of the signal, and this is also known as quantization noise power. And over here, our signal power can be defined using this formula, that is MP square by 2. MP is our message signal amplitude. So this way how we can represent our quantization amplitude. Moving ahead, at the fourth stage of quantization, what is going to happen is we want to measure a quality of received signal. That is ratio of strength of the received signal if I want to measure in terms of signal power, that is S0, compared to the noise power, that is SNR ratio. Basically, if I want to measure SNR ratio, that is signal to noise ratio, then I will require signal power value and noise power value. So S of 0 is equal to M square of t divided by the noise power value, that is MP square by 3L square, and finally the SNR value generated in form of decibel or log form will be 10 log of 3L square by 2, and its base is 10. So concluding, it is going to reduce the quantization error relatively in compared to the message signal level, and here we are using smaller quantization steps. So if this is the final stage of quantization. This is how we are going to perform the quantization at the final stage. Now, as you all might be wondering, like, what is this waveform representing? This waveform is representing two different signal waveforms, that is linear encoding and non-linear encoding. Simple linear waveform is the waveform which is directly generated without performing any coding. While this is the compressed waveform that is performed using the non-linear encoding process. So here you will be able to see two different signals in form of strong signal versus weak signal. So the compressed signal is going to be more stronger as it won't be distorted much. So this is the reason why we are moving towards compression of signal, because it is going to be kept as a compressed form. It won't be changed by other environmental factors like noise or any distortion or attenuation processes. So this is the reason why we are moving towards the compression. So this compression process can be achieved using following two processes, that is compression and expansion. Once at the transmitter side I am compressing my signal level, then back to the receiver side I need to expand it because once I had compressed it at transmitter side, but at receiver side I need to retrieve it back. So I will again expand it. So this concept is used over here, which is known as compounding process. Non-uniform quantization process, here it is represented in form of compression and expansion. At the transmitter side, we are going to uniformly quantize the compressed signal, and at the receiver side, inverse process of compression, that is the expansion process, is going to be employed to avoid the signal distortion. So this is nothing but compression and expansion of signal. Nextly, these are the references which I have referred for this topic which I have covered today. In the upcoming sessions, we will be discussing in depth the laws which are included for digital communication and what are the other modulation schemes which we are going to refer in digital communication field, comparing it with the analog modulation scheme. So following other references, you can refer for these topics which we have discussed today in this session. Thank you so much for watching this session. Thank you.